This tutoring film is about the solution of an example on slide 183 of the lecture note slide set. And in that slide set, the example reads as: the magnetization curve of a DC shunt generator at 1500 RPM is given below, where the armature resistance R sub A equals to half ohm and the field total resistance R sub F equals to 100 ohms. The total friction and windage loss at this speed is 400 watts. Part A asks to find no load terminal voltage at 1500 RPMs. Part B asks for the self-excitation to take place, find the highest value of the total shunt field resistance at 1500 and the minimum speed for Rf equals to 100 ohms. In part C, find terminal voltage V sub T, efficiency eta, and mechanical torque applied to the shaft when I sub A equals to 60 amps at 1500 RPMs. So the magnetization curve is as follows. 10 volts is the no field current induced voltage. About 1 amperes of field current, we have 170 volts E sub A. 2 amperes field current, 240 volts, and 206 amps field current, we have 260 volts induced voltage given in a graphical representation. So the same graphics is given in a more scaled and straight line, divided squares, etc. by hand, and the problem is written during the classroom lecture, so it's the same as the slide text. First, let's draw the model of this DC shunt generator. The field in DC shunt generators, the field and the armature are connected in parallel, and armature current is divided into load section where much of the current passes, and field current, which is a small portion of the terminal voltage or the current due to terminal voltage. And first, let's determine whether this machine can self-start or not. It's because it's given in the question as well. The same magnetization curve on the same curve or graphics. We draw the load line for field resistance 100 ohms, and this 100 ohms passes through 2.6 amperes and 260 volts. So this is the operating point. As you see, this is under the nonlinear curve, so it starts from this point and can self-start, as we will see. So starting from this point, the induced voltage will create some current. This current will induce more voltage. This voltage will induce more field current, and this positively feedback itself to reach the operating point B. So this machine can self-start. The starting point is A, and no load operating point is the point B. We have to take care that the same machine cannot self-start if the curve is like below. For example, this is the magnetization curve. This is the load line. So as soon as this starts, this becomes the operating point with relatively low field and very low voltage at the terminals. So this is not desired condition. So we have to take care about the magnetization curve characteristics and the load line condition going between them. So let's return back to our problem again. Part A, finding the no load voltage at 1500 RPMs. The answer for this part is obtained by using the magnetization curve. In the ideal case, B point is the operating point, where approximately 2.6 amperes field current and 260 volts induced voltage pair is obtained, but this result is obtained by neglecting armature resistant voltage drop, IA times RA sub A. So that delta VA, we call, is around 1.3 volts. Neglection could be okay. In practical operating point is roughly 258.7 volts. So this is the terminal voltage by considering the armature voltage drop, and that that terminal voltage will create field current of about 2.587 amps, or roughly 2.6 amps. So our neglection is okay. We don't do much error. In part B, for the self-excitation to take place, let's find the highest value of the total shunt field resistance. It's 1500 RPMs, and the minimum speed for when R sub F is 100 ohms. Part I assumes RF is variable, and we should find the highest value. Part II assumes RF equals to 100, so this is given, constant, and we have to determine the lowest speed. So for part A, this is the magnetization curve. This is the load line for 100 ohms. Okay, and for the same speed, 1500 RPMs, this is the critical load line to start this machine for self-start. So from 100 to higher values, the machine can self-start up to this point. So this is the highest critical R sub F value in R sub F load line. The answer for part I is as follows. The slope of the critical RF load line, which is that red line, actually in the classroom or in the other slides it's shown in magenta color. So this critical RF is 200 and found to be 224 ohms respectively. Where did we find this? This is 280 volts, approximately this amperes. So roughly, by introducing some reading errors, etc., this can be 224 ohms. So for part B, we consider for the same RF, when the speed is varied, what is the minimum speed to induce self-start? So if we increase the speed, we increase the induced voltage, because induced voltage is directly proportional to the speed. If we decrease the speed, the induced voltage is drop. Follow this curve, the voltage drop, okay, at some points the linear portion of the magnetization curves for dropped voltage will be below this line. So there's a kind of limit for the decreased speed. Again, with the graphical reading errors, we assume that this is the curve which is the critical, okay, which is the critical load line slope for 100 ohms field resistance. So the speed for this curve is roughly the half speed, which is around 750 RPMs. Lower speeds, this machine cannot self-start. The answer for part P is found graphically. This will introduce relatively large errors, but according to our characteristics drawn in the previous page, the machine can self-start at around 750 RPMs, but cannot self-start at lower speeds because the characterization curve and 100 ohm load line intersects close to origin. Part C, let's find the terminal voltage V sub T, efficiency, and the mechanical torque applied to the shaft when Armature current is 60 amps at 1500 RPMs. So, since the speed is 1500 given in the question, this is the magnetization curve. And we draw the model. Here's the armature side, and the resistor is given. So, field resistance is assumed to be 100 ohms, and armature current is given as 60 amps, and almost all parts of the current flows through the load resistance. First, we assume that the operating point is close to 2.6 amps from here, and 260 volts induced voltage point. If IF is 2 amperes, IARA is around 30 volts, because there is a 30 volt voltage drop across RA. RA is considerably large. So actually we make a little error here. IF is found to be 3.3 amps, 2.3 amps, sorry. For field current 2.3 amps, the induced voltage is around 250 volts. 2.3, so this 2.3 is given, and 250 volts roughly with graphical errors. Then terminal voltage is 250 minus 30 volts, about 220 volts. If that's this voltage at the terminals, IF is 2.2 amps, EA is 245, so this is the second iteration of finding it. So since there is a nonlinear relationship, the best method is iteratively reach the solution. Beyond this point, the solution converges. So, if we summarize, the iterative solution for this problem is 245 volts induced voltage, 60 amps induced current, 2.2 amps field current, and 60 minus 2.2, which is 57.8 load voltage, with the terminal voltages 215 points. Sorry, 215 volts. In that situation, let's calculate the efficiency. The efficiency is found. This is the net output power, load voltage times load current, 57.8 amperes for the load current, 215 volts for the load voltage. So output power can be calculated. The others are losses. Field resistance, power loss, armature resistance, power loss can be given. And of course there are some mechanical losses which were given to be 400 watts in the problem. So the efficiency equation is output power is 12.4 kilowatts. Input in the denominator, output power 12.4 kilowatts plus field power loss about 484 watts. Current is 2.2, RF is 100. Again, armature current is 60 amps, RA is 0.5. So, and 400 for rotational losses gives us 84% efficiency for the machine in the problem. Finally, the mechanical torque applied to the shaft is calculated by using mechanical power input to the system. This is the electrical power output at the armature plus mechanical losses. So EA times IA gives 14.7 kilowatts, and extra 400 watts or 0.4 kilowatts for the mechanical losses results as net power input to the system of 15.1 kilowatts. The torque is calculated by torque times the input power divided by the rotational speed in radians per second. So speed is 1500 RPMs converted to radians per second by multiplying with 30 over pi. So if we arrange everything, we end up with 1.05 Newton meters. So that ends the solution for the problem or example given in the lecture slides.